forms, can it? If I'm in charge of some sort of manufacturing process, right? And I'm tasked with trying to lower costs of manufacturing something, the best outcome is doing what? Minimizing the cost, right? Okay. Now, conversely, if I'm in charge of hedge funds for investors, the best outcome is maximizing profit, right? So optimization is really a process of what? Finding maximums or finding minimums, depending on the scenario, isn't it? Now, when we talk about things in the real world, we typically talk about something that has a well-defined domain, right? Very few things in the real world will go to infinity, won't they?
We're not doing this?
Yeah, we're not doing that. Nope, we're not doing that part. Very few things will go to infinity, right? So watch what I just created for you guys, right? If I said that most real-world concrete examples have a well-defined domain, and we can represent those things functionally, then haven't I really just created an extreme value theory problem? Because what have I done? I've given you a domain. I've given you a well-defined function. I want you to find areas of maxes or mins within a closed interval. That's an extreme value theorem problem, isn't it? Okay, so now what we're going to do, right, is we're going to create these scenarios based on some word problems. We're going to create some functions, and we're going to do some calculus to find extreme values within a closed interval. Okay, and this is the first case where you'll start to see some of this stuff happen in real life. Okay, the first couple examples, guys, are not real life scenarios. Okay, they're just kind of getting you into it. Then we'll look at one or two that are more real life. Okay. All right, so here's what we got. Our first example, very, very, very straightforward. You probably could have seen something like this in one of your regular algebra classes years and years ago, right? I want to find two positive numbers whose sum is 60. Well, right away, that sounds like a word problem where I have to create a let statement and create an equation, right? So we're going to let x and y a positive number all right, got two positive numbers, right? And I get the condition that the two positive numbers have to have a sum of 60. And then again, when you got to read the problem contextually because it's the way it's written. This next phrase kind of has to be read with the beginning phrase. So it says, find two positive numbers whose sum is 60 and whose product of one times the square of the other. The product of one times the square of the other. What's that sound like? The product of one times the square of the other. Squaring what? First of all, it says the product of, right? So what am I multiplying? Two things, right? What are those two things? The product of one times the square of the other. X times y squared. Yeah, xy squared. Right? So we have xy squared is a maximum. Right? So let me give you this scenario, right? Give me two numbers that have a sum of 60. 30 and 30, make them not the same. 27 and 33, right? We all agree that 27 and 33 will add to be 60. No doubt about it. So if I take 27 and multiply it by 33 squared, I get some value, right? Now there are other combinations besides 27 and 33. My question is, which combination will give you a product of xy squared that is the greatest possible value? Sound good? You're guessing 29 and 31? Okay, might be. We'll find out, okay? So here's what we want to do. We want to maximize this, right? We want to maximize this. So it's a maximum on what domain? What are the extreme scenarios? What could x be? Could be 0 up to 60. Yeah, so when x is an element of 0 to 60. Now that part of it was not part of the original question, was it? But the domain is created by the parameters set in the problem. Okay, what's our issue? Our issue is that we have two variables here, right? But can't this condition be solved, plugged into this condition in order for us to get one variable? Kind of like a system, right? You want to solve for x or y, choose. All right, Week says we're going to solve for x. So x would equal 60 minus y. So what am I going to do now? I'm going to take this and I'm going to plug it in here, right? So when I plug it in there, I get 60 minus y times y squared. And we want to maximize this now. Maximize, try to spell that right. What did I just change, by the way? What did I just change? I changed what? I changed x to y when I talked about the domain, right? Because my problem now is y's in it instead of x's. So it's really when x or y is between 0 and 60, correct? Yeah. All right, so what am I going to do, guys? I have a function, right? I have a closed interval, and I want to know the maximum value. That's a perfect example of the extreme value theorem that we did at the very beginning of this unit. So how do I determine the extreme values? I differentiate, I find critical values, and I figure out what those values are along with the values of the endpoints. Okay? So we're going to determine d dy of, is it okay if I distribute the y squared? So of 60y squared minus y cubed, right? So find the derivative of this, right? What's the derivative? 120y minus 3y squared, right? So there's my function as a derivative now, right? So what do I want to know about the derivative? I want to know the critical values. And what are critical values? Where a derivative equals 0 or does not exist, right? So the critical values are going to be where this equals 0, right? What is that? 40 minus y. So I have two critical values. I have a critical value of 0 and a critical value of 40. Agreed? All right. You guys all told me that 0 to 60 are the numbers that make sense here, right? So if I was to actually create a quick number line, and I did my analysis, right? So if I did my analysis now, give me a value between, by the way, does this 20 really make any difference? That's just there, just as a placeholder, right? Give me a number between 0 and 40. 20. How about, I like 1, right? Yates said 1. I like to make my life as easy as possible. So I'm going to plug into my derivative, right? So if I plugged in 1, I get 120 minus 3. This is definitely going to be a positive interval here, right? What does that mean? It means my original function was increasing from 0 to 40. So f prime is greater than 0 when x, actually I'm not using x, I should say what? When y is an element of 0 to 40. So I'm increasing, right? Okay, what's happening at 50? That's going to be 600 minus what is that, 16? It's definitely negative, right? Definitely negative. So this is definitely a negative interval. So f prime is less than 0 and y is an element of 40 to 60. So does that follow the things that we need in order for this to be a maximum value? I'm seeing heads shake yes. Why is it a maximum value? Because what was I doing in the interval prior to it? Increasing. What was I doing in the interval after it? Decreasing. So 40 must be a maximum. Now, really quickly, guys, if x, and here's, I'm not going to test 0. Why am I not going to test 0 even though it was a critical value? If y was 0, what's the product? 0. And this gave me a positive number, right? So if I have a positive number and I get here and then I start going down, right? So I'm increasing, decreasing. This has got to be a max. 0 is not going to work. Am I going to test 60? Why am I not going to test 6? Why am I not going to test 60? Because if one number is 60, then the other number had to have been 0, right? So the only possible value that makes any sense is the 40. So what did the two numbers have to be? 40 and 20. Is that cool? Right? Kind of a nice example, right? Just to get us into the swing of things. Anybody know what the optimal area is of a rectangle? So it's a square. Yeah, of course, right? The biggest area that you can create given a rectangle is that of a square, because a square is a rectangle by definition, right? Yeah, so that's what we're going to have here. We're going to prove that here, actually, okay? So I have a piece of pipe cleaner. Pipe cleaner is the bendy, fuzzy things, right? And it's 8 inches long, and we're going to bend it to create a rectangle. So what does that mean? It means I have some rectangle. Do I know the dimensions of it? No. So what am I going to call them? Length, width, length, width. What's the constraining piece of information? What's the limiting factor? The length of the pipe cleaner, right? Sounds like a perimeter, doesn't it? If I'm bending it to create a shape. So can we all agree that the perimeter of 8 is equal to 2L plus 2W? Right? The two lengths plus the two widths has to give me a total perimeter of 8. But what am I actually trying to accomplish? Am I trying to maximize the perimeter? I'm going to mind up making it a square. Let's pretend that we didn't know it was a square, right? Let's pretend that it's some shape, right? So I'm trying to maximize the area, correct? Yeah, so we want to maximize, yes. We want to maximize the fact that area is equal to length times width. On what interval? When L and W are elements of an interval that goes from 0 to 8. Now, if I wanted to put a closed interval on there, I could, because I could what? I could either choose to not bend the pipe cleaner, in which case I actually don't have an area. So 0 and 8 are values that we're going to consider, but at the end of the day, do they matter? No, because 0 and 8 do not create a rectangle. Okay, so testing the endpoints, not going to be necessary here. Okay, I want to maximize this, which means I want to differentiate this. But the problem that I have is that I have two variables. So what am I going to do? I'm going to solve this for the variable of my choosing, plug it in here so I have one variable, and differentiate that way. Sound good? All right, so what do you want to solve for, L or W? We're going to solve for L. All right, so L is equal to 4 minus W. So if I go back to this, that's what I'm trying to maximize. Can I make that look a little nicer? Or W minus W squared, right? All right, so what am I going to do now? I'm going to differentiate And that's going to give me 4 minus 2w. There's my derivative, right? I want critical values, which means set the derivative equal to 0. And that means 2 is a critical value. All right, so what do we do? 0, 2, 3, 4, 5, 6, 7, up to 8. All I'm really concerned about is what? Here, that interval, in that interval, right? 0 to 2, 2 to 8. Because I only have that one critical value. So we're going to do our analysis to make sure, right? We got to make sure that we what? Went from increasing to decreasing because we're trying to do what? Maximize, right? Maximize means increase to decrease. So if I plug 1 into the derivative, I get 4 times 1 minus 1, positive value. If I plug in 3, I get 12 minus 9, also positive value. Oh, I didn't plug it in the derivative, sorry. Yeah, I'm looking at this, I'm like, hang on a minute. Sorry, we gotta make sure we plug into the derivative, this one. Plug in 1, we get a positive value here, 4 minus 2. Plug in 3, we get 4 minus 6, which is negative. There we go. Yeah, we gotta make sure we plug into the derivative, not the original function, right? Don't make that mistake that I just made. Okay, so what do we have? We have an increasing interval from 0 to 2. We have a decreasing interval from 2 to 8. That means 2 must have been a maximum, so we have a maximum area. So the max, what does it say? What dimensions will produce the rectangle of the maximum area? 2 by 2. So far, so good, right? Again, very, very straightforward examples thus far, right? So what kind of a question can I give you that isn't as obvious? Well, here we have a ladybug farmer. I don't know, guys. And the ladybug farmer has 5 inches of fencing and wants to fence off a rectangular field that borders up to a straight river. So I got a river. Right? And it's perfectly straight. And I want to take my 500 inches of fencing and I want to create an enclosure that butts up next to the river such that the river serves as one of the boundaries because ladybugs can't swim and the farmer has clipped their wings. No, we clip wings. People clip wings all the time. Nonetheless, we have 500 inches of fencing, right? So again, it says that we want to maximize the area. We want to give the ladybugs as much room as possible to enjoy their lives, right? So we're going to call these widths still, right? We're going to call this a length still, right? Is it really a perimeter per se? What's the limiting factor here? The amount of fencing that I have, right? And the fencing is only used on the widths and the one single length, right? So it's going to be 2W plus L equals 500. That's our limiting factor, right? That's our restrictive item, the amount of fencing that we have. We're counting, yeah, this is just, that statement right there represents the amount of fencing that I have. Correct. The river is a boundary. Would you guys agree that the area is still LW though? Right? Still length times width. And that's what I'm trying to maximize. Is there a domain here? Is there a least amount of fencing that I could use for W? and a greatest amount of fencing that I could use for W. Yeah, what could they be? Anywhere from 0 to 500, right? So we're going to maximize it on that domain. And of course, another perfect example of where I don't need to really consider the endpoints, because 0 and 500 will do what? Not create an enclosure, right? So very similar to the last couple of examples, I'm going to solve for one of the variables and plug it into my area formula, right? What are you going to solve for? Very good. So L equals 500 minus 2W. We're going to take that, and we're going to plug it in. And that's what we want to differentiate, and that's what we want to maximize, right? So I have my derivative, or no, I don't. I'm going to have my derivative right now. $500 minus 4W. Critical values are found when I take that and that equal to 0, good. And we get W equals 125. We're going to save ourselves a minute of time here. No, I'm not. 0, 125, 500. If I plug in 1, what am I plugging into again, guys? Derivative. If I plug in 1, what do I get? Positive or negative value? Definitely a positive number. If I plug in 400, what do I get? So did I increase up to 125? Yep, because the derivative was positive. Did I decrease after 125? Yep, so 125 must have been a maximum. So what are the dimensions? The width is 125, the width is 125, which means the length is 250. Yeah, when we come back from break, we're going to talk about a minimum. So here's the thing, Pardeep. I used to have a Pardeep. Hardeep, same last name too. Was Pardeep a cousin? No, I had a Pardeep Daliwa. Sorry, I'm just not used to seeing you. So so the thing is this: if I tried to minimize this, I could almost minimize it so that there's an area of how much? 0, right? In fact, trying to minimize this would actually not be possible, because what did we do? We did the exact same thing that we would do if we tried to minimize it, didn't we? Is there a minimum value? Do I ever go from negative to positive? No, so there is no way to minimize this, because the actual way to minimize this would be to what? Approach 0 or approach 500. But why aren't those minimums then? Because I can't ever get to 0 and I can't ever get to 500. Because if I got to them, what would happen? I'd no longer have a rectangle. Make sense? Okay. When we come back from break, guys, we're going to do this problem below, which is kind of an extension on the one that we just did. And then I'm going to show you something that is really concrete that you could actually do in a job someday. All right. I'm going to make you a worker at Pepsi or something like that. And we're going to talk about aluminum cans. All right, back to the ladybug. New example. Similar kind of scenario. All right, so the ladybug farmer, from their infinite level of expertise in the field found that if there is 10,000 square inches of grazing, they'll be in their optimal state. So we want, yeah. So we want the area now to be 10,000. So now my question is this. Yeah, we could get 10,000 really easily, right? We could do 10 feet by 1,000 feet, right? That would work. Or we could do 100 feet by 100 feet, right? Or no, 100 by 1,000, right? And that would work. Or no, hang on, not 100 by 1,000. I was right the first time. 110, right? 100 times 10, that would work. But, oh no, 100 times 100. Yeah, we got it, 100 times 100. But the point being, that's the optimal dimension, right? So what we need to do is we need to figure out what is a least amount of fencing scenario, right? So what width and length using the least amount of material will give me the optimal area. Get the idea, right? So we have a W and a W and an L. Well, we still know that our length times width is our area, right? And what do we want that to equal? We want that to equal 10,000. What are we trying to optimize here? We're trying to optimize the perimeter, the amount of fencing, right? So we want to minimize the perimeter. Not really perimeter, I guess, but sort of like a perimeter. So we want to minimize the 2W plus L. That's what we're trying to minimize. So what are we going to do? Well, we're going to do the opposite of what we did on the previous problem, right? We're going to solve for this one, plug into this one, and then what? Differentiate and optimize using that second function, right? So this is where you see how, you see which one you're differentiating, the difference between the two examples, right? What do you want to solve for? L sounds good. Going to take that, going to plug it in. All right, so this is what we're trying to minimize. So we're going to DDW. Okay if I write it like this? I just like it that, I like that better, right? Don't you? So when we differentiate, we get 2 minus 10,000 W to the negative 2. Okay, so let's let's make it look nice and then figure out critical values from that, right? So if I make it look nice, I get that. And if I put these two things together, I need a common denominator, right? So is it okay if I make this 2W squared over W squared? That would then give me a common denominator. That's equal to this. Okay. So this is an example where our algebra is a little bit more complex, right? Okay, so critical values occur when derivative equals 0 or does not exist. So one of the critical values is going to be 0. We already knew that was a value that we would consider because that would be one of the endpoints of the domain here, right? But again, do we really care about the 0 in this case? No. Do we really care about the 500 in this case? Or I'm sorry, not the, oh, wait, hang on, get rid of that. Do we really care about the 0? No. Why do we not care about the 0? Because if we had a 0 for this or a 0 for this, we would have an area of 0, right? So we know that even though this is a critical value, it's not going to matter. Okay? So we'll take the numerator and set it equal to 0. And we get a solution of radical 5,000. Now, what are we going to do here? Well, if we did this, so if we did an analysis starting at 0 to radical 5,000 to, I'm going to put infinity. Is that okay? Because do I really know what that other dimension is going to be? I don't, right? So I'm just going to put a value just bigger than 5,000, in other words. All right, if I plug 1 into the derivative, what do I get? Positive or negative number? Plug in 1 and I get a negative value. All right, if I plugged in 5,000, what am I going to get? Definitely a positive number. Not radical 5,000, but actually 5,000, right? So what happened? I went from a decreasing value to an increasing value, which means this must have been a minimum value, and so we found the minimum width that gets us this area, right? So our W value is radical 5,000, which means our L value is 10,000 over radical 5,000. And of course, if you had to rationalize that, you would. I'll leave it like that because I'm lazy. Oh, the least amount, right? The actual question said, what is the least amount of fencing? So what am I going to do? Multiply this by 2 and add it to that, right? Yeah, so the fencing is what? It's 2 W's plus an L. So the least amount is 2 of these plus 1 of those. How you doing? Happy? I am. I'm very happy. I'm going to come back to 5 and 6. I want to skip ahead because I promised you guys that I would do a problem here. Oh yeah, no, we're going to do it. We got time. We have plenty of time. So I want to give you that wonderful example that I think is a pretty good one. And this is like one of those problems we're going to see is an AP style question, okay? We have a cylindrical aluminum can, right? And most aluminum cans hold 12 ounces of liquid, right? So our task is to do this. We want this can to hold 12 ounces of liquid, and we want to use the least amount of aluminum possible. So my question is, what size should the cylinder be? Got it? So what are the things that are going to go into this problem? Well, I want to use the least amount of aluminum. So what does that require me to compute? Okay, so I heard volume, I heard height. The surface area, right? Isn't the surface area going to be the volume? I'm sorry. Isn't the surface area going to be the aluminum, the amount of aluminum used? Right? The other constraint that is part of this problem is the fact that given the amount of aluminum that I have to reach a particular volume, right? And that volume is 12 ounces, right? So here's what we got. We have a surface area formula. And the surface area of this object is going to be what? Well, I have a top, which is a circle. And how do I find the area of a circle? Pi r squared. Well, how many of those are there? There's 2 of them. Now I know that, yeah, the one on a can is not flat. You guys know why it's not flat, by the way? You know at the bottom of anything, glasses, right? this, right? Why is it not flat? Yeah, if it was flat, putting it down would eventually weaken the bottom because of the pressure, the way that the pressure would impact the flat surface. So the domed surface allows that pressure to equalize. Yeah, so same thing with this, right? All right, so we have two circles. We got that. Okay, what else do we have? Well, we have the side, right? Well, what could I do? If I was to take the top off, take the bottom off, and cut a vertical line, roll it out, and what shape do you have? A rectangle or a square, yeah. And what is the dimension of that rectangular square? Well, it's the height times what you get when you roll it out, which is the same as the circumference of the circle, right? How do you find circumference of a circle? Pi times diameter, or 2 pi r, right? So do you guys agree that the one dimension is 2 pi r and the other dimension is the height, right? So that's going to be your width, that'll be your length. All right, so we have a formula for surface area. Volume of a cylinder is pi r squared times h. Quick question. I have two formulas here, right? Which is the one that I'm trying to optimize? The surface area, right? Because I want to use the least amount of aluminum, right? So this is the one that we're going to optimize. All right, cool. What's our constraint? What's the thing that's going to constrain our optimization? The 12 ounces, right? The amount of liquid that I need to hold, right? Now 12 ounces is actually a different, like, it's not going to be in terms of what? It's not in the same unit here, right? Because they give me the fact that the can is what? Is, let's see. Yeah, so it gives me some information about inches and wants me to compare in inches. So there's a conversion for us, right? The actual volume of 12 ounces is 21.6562. All right, cool. Well, what did we do with the other problems when we got to this point? Well, we solved for something and we plugged it into the other one, right? Because if we're trying to optimize this, we only want one variable. Well, I have an R here, I have an R here, I have an H. I can solve for R or H. Which one do you want to solve for? Yeah, I think H is better because if I solve for H, I'll have R's and I'll only have to substitute here once, right? Seem cool? So we're going to solve for H. And then what are we going to do? Well, we're going to take this and we're going to substitute it right there. I can actually make that look a little bit nicer, right? Because what's going to happen here? Pi and pi r and the squared. So surface area is that. I'll stop there because it's going to take us a little bit longer, okay, to finish this one up. So we'll stop there.